Okay, so now we're doing an introduction into polynomials, and so we are starting. Okay, so a polynomial is basically term a series of like a function with um, various coefficients or various numbers multiplied to various powers of x, and they're all added together in strings or in groups, and yeah, so overall, a polynomial has the form, let's see, a(n), so the nth term of a, um, x times x to the n, so it's some constant multiplied by x to the nth power. N can be any number, any whole positive number, so any natural number in a sense, plus a n minus 1 times x to the n minus 1. So this is the n minus 1th coefficient. That's what we call these, the coefficient of x. So the constant term that's multiplied with x. And so we have x to the power of n minus 1. So you notice that it's one less than the term before it. Plus a n minus 2, x to the n minus 2. And we get so on until we get a 1x to the 1, but x to the 1 is just x, plus a 0. So this is our constant term because it's multiplied by basically x to the 0, which is just 1, so it's just a to the 0. Yeah? Yeah. Where an is, so where a base n, wait, yeah, not base n, a subscript n, or an can't be equal to 0. Because if an is equal to 0, then this whole term becomes 0, and this becomes our new an, you know? So the idea of a n minus 1 is pretty redundant if we don't have an an. You know what I'm saying, right? So an can't be equal to 0 because we don't have any leading term, kind of, you know? So the highest power of x is basically a point of interest to many uses of polynomials. Because when x gets really, really large, or really high in magnitude, either positive or negative, it's this term that takes over the most, right? If we have like if we had like if we compared if x was 10 and n was like various powers, so if I made this 6 and then this is 5 and 4 and 3, it's the 10 to the 6th that will be much larger compared to the previous terms. Anyway, so the term with the highest power is what we call the leading term. Again, yeah, we like to keep it a nice fancy name, so we call it the leading term. Leading term. And so the coefficient of the leading term, this term, is like what we call the leading coefficient. Okay, so if the leading coefficient is 1, we like to call this whole polynomial as monic. Mono, related to 1. So monic is where our first leading coefficient is 1. And it makes things quite simple when we're dealing with monic polynomials. Often it's used as like a stepping stone example, which then we further into like more complicated examples. Anyway, so if all the coefficients are real, so all the coefficients are these numbers, if they're all real, the polynomial is said to be defined over the field of real numbers, and it's denoted by r, like this, kind of like that, something like that. Yeah, it has the two lines and it has the weird r thing, and that's where it says it's part of the set of all real numbers. Okay, if the coefficients are all rational, the polynomial is said to be defined over the field of rational numbers. Yeah, or if preferred, the field of real numbers. Anyway, okay, so then I'm going to start introducing the types of polynomials that we are most going to be familiar with. So we have a linear polynomials, linear, and these are given by p of x. So our polynomial is a1x plus a. Well, you may be familiar as this is like the equation of a line. It basically mirrors that, y equals mx plus b. B is just a constant, a is just a constant, a1 is just some number multiplied to x, and m is some number multiplied to x. P of x and y would so the form here is very, very similar, and this is why we call it a linear polynomial, because this is the when graphed it would make the y equals mx plus b, because they're both one and the same. They're just numbers multiplied to x and added, and when plotted it will make a line. We have a quadratic polynomial, and is defined as p of x equals a2 x squared plus a1 x plus a. Yeah, and so then we see it's just like an extension kind of linears. So then we have our highest power of x as x squared, and our leading coefficient is a2 instead of a1. So we get when graphed as such, we get a parabola. Either it will curve like up like this, or it will curve down. And the various letters and will decide which way the parabola is facing and the position of where the parabola is. When we have our highest power as 3, so we have our highest power here as 2, highest power is 1. When we have a highest power of 3, so a3x cubed plus a2x squared plus a1x plus a. When our polynomial is defined as such, we call it a cubic. You know, like a cube is a three-dimensional shape. There's a lot of threes starting up, so you know you kind of see a relation over here. Anyway, so this is what we call a cubic. A cubic's shape looks like such, and it has like a bend. It actually gets horizontal in a sense, and then it comes back up, so it's a more accurate version. And it goes, and these are my axes. When I graph such a polynomial, it will have like a bend kind of shape. Yeah. So a polynomial of degree 0 is just a constant. So if my highest power of x was just 0, then I'll just get an a, yeah, which is just my constant. And a constant would just be a horizontal line. So if I have my axes, my constant polynomial would just be a horizontal line. For all values of x, it's just going to be that one constant. That's why we call it a constant, because it doesn't change. Anyway, we can also write our polynomial p of x as a sum in sigma notation, because sigma notation is always used for summing up things, because it really compacts everything and it just simplifies. You know, instead of using like one really long, this extremely long method, we can just condense it into sigma notation, which is the sum, or sigma, from k equals 0 till n of ak x to the k. And basically this just says the same information as this guy up here. Yeah, so sigma, because everything's added up together. See, there's a plus here, and so on. And so we would have our various coefficients of x to the decreasing powers of k, or decreasing or increasing, matters which way you think. Because say if I read from right to left, like I flip it over, because they're all added, so I can flip it all over and then I can do the same thing. Anyway, so next up, okay, so the number c, well, it depends, it's like not always c, but the number c is called a 0 of p of x, if p of c is 0. So say if I tell you that p of 0, okay, so if I say, no, not p of 0, sorry, if a1x plus a equals 0, then what x value follows this rule? And whatever x value, I'm going to call it c. So c is the special number, in which case, so if x equals c, right, p of c is equal to 0. That's the special thing about c. And this is what we call c a 0, because it generates a result of 0 when we plug it into our polynomial. Not all polynomial equations have real roots. The roots of a polynomial equation give the intercepts of the x-axis of the graph of the function. So essentially, we can denote a polynomial in a second way as p of x is equal to some constant multiplied by x minus alpha, x minus beta, so on, right? Until we reach our last one. And if any one of these is equal to 0, then because they're all multiplied together, they're all going to produce a value of 0. And if they all produce a value of 0, our p of x is our y value, right? So if any of these values become 0, we get an x-intercept. We have our graph touching or crossing the x-axis as y equals 0. Anyway, let's see, next up. So for very large values of x, either positive or negative, as I stated before, our leading coefficient will take over. The polynomial of an odd degree has at least one real 0. So if I have my polynomial, right, and if my highest power of x was is an odd number that makes an odd polynomial, then it will always have at least one real 0. So it will always cross the x-axis in one place, at least once. A polynomial of even degree may have no real zeros. So say if I have my little parabola here, right, and my x-axis was here, right, it may just not at all cross it, and it may not have a real 0. A 0 is where it crosses or touches the x-axis, right? So there are instances where it may not. But if I have like a line, right, if I have my axes again, and if I have a line, right, I will always end up crossing the x-axis, unless it's a horizontal line, but that makes it a constant, which doesn't make it exactly a line. If I have a cubic, it will always have like the S kind of shape. It will always, at some point, no matter however I shift it, it will always cross the x-axis at least one point. That's what this dot point said. Anyway, at least one maximum or minimum value of p occurs between any two distinct real zeros. Okay, so if I have a 0 here and some other 0 here, right? And okay, I have to have a polynomial that has these two zeros, right? I can have a cubic, for example, and it goes up like this, something like that, yeah? I will have a maximum value of x, like a relative maximum between those two roots, which is like around here, right? If I have a parabola downwards, right, I have my relative minimum down here, yeah? So it's always between two roots. That's what we must recognize here. Okay, so now after introduction, after you met this guy, and then we got to learn how to do stuff with it, yeah? So then let's try adding and subtracting, right? So any two polynomials can be added or subtracted, and it will give another polynomial. So if I have, let's see, go away. Okay, fine. If I have 2x plus 3, and if I add that to, not multiply, add that to x plus 5, yeah? This is just gonna get me another polynomial, p of x, right? And in this case, p of x would just be 3x plus 8, which is just, yeah, again, as I said before, it's another polynomial. If I add, say, a quadratic, so it's x squared plus 2x plus 5, added to 2x plus 3, right? My resulting polynomial will have the highest power of x of either of the two. You see how I have a quadratic, so the highest power is 2, and here I have linear, so then my highest power is 1. So between 1 and 2, the highest one is 2. So the highest power of x that we get is 2. So we get x squared, then we get plus 4x plus 8. So we notice that we have our highest power of x is the, so if I'm going to make a generalization, p of x plus q of x. The degree, so the degree is the highest power. So the degree is the maximum of either p or q. So the highest power. Yeah. If yeah. So if let's see. If the two wait. Oh, whoops. Okay. I think that I think it's a typo in the sheet. Sorry. So if I have the same highest power now, say if I'm taking another example, x squared plus 4x plus 5, and if I'm subtracting it with, I don't know, x squared minus 2x plus 1, right? So whenever when I'm subtracting and the highest power is the same, then like yeah, so when the highest power is the same, the resulting polynomial, so I'm going to call this p of x. Now my resulting p of x, not r, it's p, sorry, p of x. P of x will have a degree less than or equal to the original polynomial. Because imagine if it's a 3x squared, then I'll end up with a polynomial that has an x squared in it. In this case, then we'll have the x squares cancelling out, so my highest power would be an x. So it will always be equal to or less than the either of the two, or the highest of the two. If I mean less than the highest power, which is the same. Kind of get it anyway. So now on to multiplication, right? If I'm multiplying two polynomials, so if I have ax squared plus bx plus c, so this is a general form of quadratic, multiplied, I don't know, mx plus b plus, k, yeah, right? The highest power of my polynomial will be x cubed. So the degree of this, so I'm going to call this degree m, and I'm going to call this degree n. So in this case, m is 2 and n is 1, right? So the degrees end up adding together. You see how we have ax squared plus m times mx, because when we do the expansion, right? So then we get a mx cubed, right? And the highest power we can possibly ever get is an x cubed. And we can only get that from multiplying the highest powers. Yeah, so when dividing two polynomials, we do not always get another polynomial, unlike the other cases, right? A polynomial must have a positive, it must have all the terms with positive degrees of positive powers of x. Yeah. Okay. Yeah. So like a few examples, right? Actually, I don't know, should I do these examples? Don't think so. Yeah. So overall, this is the description of our polynomials. Actually, I'll go into division a little bit. Yeah. So say if I have ax plus b all over, I don't know, mx squared plus kx plus 2. I don't know. I'm giving some numbers, some values, right? mk, 2. They're just some numbers. I'm just making some arbitrary example, right? Then this is going to be like a highest degree 1 over a highest degree 2, right? And it's like we're going to end up with some weird fraction, right? And we're going to end up with some remainder. And our remainder isn't going to be it's not going to be it's not going to be exactly a positive whole number power of x, right? And if we don't have a positive whole number power of x, our whole resulting function isn't exactly a polynomial. Yeah. Yeah. Basically, that should be it. Yeah.